Today's lesson, section 9.2b, the dot product. We're still talking about that. This is part 1 of section 2b. Here, we want to kind of shore up some other things with dot products and vectors. One thing is that sometimes you'll be asked for a unit vector. Okay. Now, a unit vector is a vector that's kind of like you could put on the unit circle, basically. Okay. So you are recalibrating the magnitude of the vector so that it has kind of ends up being or it could be mapped on the unit circle, basically. Okay, so that's why it's called a unit vector. So a unit vector is the vector of u divided by its magnitude. Okay, now, or you could write it a different way, where if you have a vector of u, and let's say that your values are a and b, then you can divide each of those individual values by the magnitude. So it's almost like saying, remember, if this is a ordered pair, this is like your cosine over your x over your r, and then this one, b, is your y over your r. Okay? So just like we would use in a unit circle, ordered pair point. Okay? So example 4 says find the unit vector in the direction of 4, 6. Okay? So first, you need to find your magnitude. So let's call it vector A. Doesn't matter. And I want to take the magnitude of it, because that's the first thing what we need to know. So 4 squared plus 6 squared gives me 16 plus 36. So then 16 plus 36 gives me 52. Now that can be simplified because you can have a 4 out of there, so you could say 2 squared of 13. So then that would be your magnitude. So now plugging that in, if I'm going to write it the second way, I would say that my vector A would be my x value, which is 4, over 2 square root of 13, and then comma 6 for my y value over 2 comma square root of 13. Now it looks like for both of these they both have a value of 2 in common, so I could reduce and take out a 2. So reducing that, take out a 2. So that gives me 2 square root of 13 comma 3 over square root of 13. Okay, and that would be an example of my unit vector. Okay, for this example. Example 5, they said find the unit vector in the opposite direction of negative 2 comma 5. So what that means is that, so we want to first find our magnitude again, so let's call this u. So square root of negative 2 squared plus 5 squared is going to give us 4 plus 25. It's going to equal 29. Okay, so there's our magnitude. And then, if we want to do opposite direction, that just means that for our vector that we currently have, opposite direction, think of this as slope. So you're going to go 2 to the left, up 5. So the opposite direction would be to change the opposite signs for each. So it's like multiplying by a scalar of negative 1. So that puts you at 2 comma negative 5. So if you graph this visually, this will help confirm that notion. But now I would just do the same thing I did in example 4 with my adjusted vector and my magnitude. So then now my unit vector for u should be 2 divided by square root of 29 comma negative 5 divided by square root of 29. Okay. Example 6. Here I want to find a vector of length 4 in the direction of -1, -3. So here, same thing, start the same way. I want to take the magnitude of my vector, so -1 squared plus -3 squared is going to equal 1 plus 9, which equals the square root of 10. Okay, and then I would do the same thing as I would normally do. So take your a and b value and divide it by your magnitude. So you get -1 over square root of 10, comma -3 over square root of 10. Okay, but because you want it to be a length of 4, okay, so realize that now your magnitude is at length 1. Okay, when you make a unit vector, it's, since you're putting it on the unit circle, your radius is now 1. Okay, so when I want to change the length, if it wants a vector 4, I take my 1 and I times it by the number of the magnitude they want it to be, because anything times 1 is going to be that something. So 4 would be our new scalar. So now I'm going to multiply that scalar through, so it gives me -4 over square root of 10, comma, -12 over square root of 10. And so then that would be my new vector of length 4 in the direction of -1, comma, -3. Okay? Now here, we're going to talk about something new. Component of u along v. Now, the component of u along v is talking about a vector that is in the, like, it makes up your u. If you remember that, and it would be better with another picture. Let's say, let's go to a different video. Okay, so there you go. So if I have a vector, okay, and then I have another vector, okay, remember if I add them together, then that makes it go out further. So like if I added it here, or kind of like when we're graphing, or added it there, you know how we make this new kind of vector? So let's put it in green. Okay? So notice that there's components or parts of your vector. So it's made up of an x value plus a y value that create this vector, basically. So when we go back and talk about a component of a vector u along v, that means that if I'm looking at u's vector, okay, it has a x component and a y component. So basically for this one, when you're talking about a component of u along v, you're talking about the part of u, or the component of u, like for your vector, that actually makes up, or it comes from vector v, okay? Because there's also this y1 over here, right? But we are not really concerned with that one. We're just talking about this part right here. That if I put it with my y, makes this vector u, okay? So that's kind of what we're talking about. And it's kind of, you can kind of think of it as a shadow, because your u vector is always going to be like casting, like it's going to be straight down, so it's almost like casting a shadow onto vector v. So the reason why vector v is important is because like the component of u is actually kind of a portion of vector v. That's why we call it r times vector v. So r represents a scalar multiple that if you multiplied it to vector v, you would get the part of the component of u that we're talking about. Okay? So the definition for sure is the magnitude of the portion of vector u that points in the direction of vector v. That would be this little smidgen right there. Let's put it in red. So like if I was doing this vector right there in red, Okay? That's what we're kind of talking about. So we can define this as the magnitude of u times cosine of theta. Now this, because it's a component of u, you're talking about a scalar. So it's not a vector, it's its own like just number, because if I was to make u, like put it in ij form, okay, it's this part, that a value that we were trying to figure out. Okay, we don't care about the b value, but it's a scalar because it's just a number attached. It's the number that we're finding is attached to I, but it's just the a, no I. Okay, so it's no vector, and it can be in any direction, which is what this picture over here is trying to show. So it could be in the opposite direction, just depending on what your theta is. Okay. Now there's different ways of calculating it. We can use our angle in between two vectors formula to help us kind of make a calculation formula. So since we said that the scalar is the magnitude of u times cosine of theta, it's almost like just multiplying this magnitude u to both sides, okay? Which leaves us with the dot product over magnitude of v. And that's going to be kind of our calculation, because sometimes it's easier actually to deal with that rather than trying to find your angle. Now if you're given your angle and you know the magnitude of u, then certainly we can use this. But most of the time, the second one, the dot product, and the magnitude v is actually easier to find, because then you don't have to worry about doing the inverse cosine of anything. And plus, that information is usually more readily available. Okay, so example 7 says find the component of u along vector v and the component of vector u along vector v given, sorry about that, this one is backwards because I want to kind of do both ways. So let's rewrite that. So I want to find the component of vector u along vector v, and I want to find the component of vector v along vector u. So I kind of go both directions. Okay? So if I want to do vector u along v, then that just means that it's your dot product, okay, with, and it's always going to be the magnitude of the second one here, okay. Now if I want to do it the other way, then it just means the dot product's the same. It just means that it's going to be the other one. If you want to, because dot products are commutative, you can switch the order so it makes more sense if you'd like. Okay, so let's do our dot product. So dot product of u and v, so 3 times -2 plus 4 times 5. And then the magnitude of v is going to be -2 squared plus 5 squared. Okay. So then that's going to give me -6 plus 20, which gives me 14. And then at the bottom here I get 4 plus 25, which is square root of 29. Okay? So then that would be the component of u along vector v. And then down here, now the dot product is going to be exactly the same. So, because remember it's commutative, so I already know it's 14, but the magnitude is going to be different. And take 3 squared plus 4 squared. So 14 over square root of 9 plus 16, which here, square root of 25, which is going to be 14 over 5. Okay? So then, that's kind of how we do or find the component in either direction. It doesn't really matter which one you're doing. Just make sure that the one you're going along is the magnitude that you're using. Okay? That's kind of like that R component of our value there. Okay, next part we're kind of talking about force. Now, here kind of mainly focus on like vehicles on an incline. So let's say that the vector W is the weight of the car downward, so gravity. Vector V is the force experienced by the surface of the incline, so kind of like the driveway. So these are always going to be like on the side of a hill, almost. And vector U is the force of the car that's trying to pull the car down the incline. And so remember that vectors U and V add up to make W. Okay. So the magnitude of vector U and vector V are components, like I was trying to say, add up, of vector W along vector U and vector V respectively. Okay. So the component of W along U is kind of like what we were doing before. Okay. So example 8 says a car weighing 3,000 pounds is on a driveway incline at 15 degrees. Find the magnitude of the force pulling the car down the drive, and then find the magnitude of the force exerted on the driveway. So we're kind of trying to find U and V. Okay. So, and you're already given W. Okay. So for this one, if I want to find A, so that would be the component of W along U. Okay, that means that we're taking the dot product of U and V, and then the magnitude of U. Okay, so here, now also, remember that this 3,000 pounds also gives us a vector as well. So since you're going straight down, the vector does not move left or right, so your x value is 0, and you're going straight down, so it's like a negative 3,000. Okay? So it does give us something like that. Now, they also say, remember, go back to our earlier thing when we were looking at our calculations. One too many. Oh, yeah, right here. Okay, so notice that these two things are equal to one another. Okay, so we don't have to just use, because you don't really know the component of U if you look back here, right? So we don't really know the component of U or like the vector of U or the vector of V, but we do know an angle, theta, and a vector value of W. So we could use the magnitude of W times cosine of theta. Okay, so since I know those things, we can say 3,000 times cosine of, and we need to figure out that angle measurement, right? So if we go back to our picture, or make a picture, so if the incline is 15 degrees, and here's your car, sorry for my poor drawing skills, okay, then that means that this angle here, okay, straight down, so this part is 15, okay, but it's the angle at which U is looking at, so this is U over here, so this one is going to be 75 because here is a 90-degree angle, so completing the triangle. So that's the actual angle that you want to use. For the other one, for V, you'll use this part, and so that one will actually end up being 15 degrees. So you have 75. So if I punch that into my calculator, I get 776 pounds. That's the force. Okay. Letter B wants the component of W along V. Okay? So same thing. We could use that calculation formula that we've been talking about, or we can use this one since we do have this information. So this one, like I was saying, V's force is at an angle of 15 degrees in between your two angles. Okay, so notice that I'm using the angle in between my two vectors. U and W's was 75, and V and W's will be 15. So still 3,000 magnitude cosine of 15 degrees this time. So when I plug that in, I'm going to get 2,898 pounds. Okay? In our last example here, I want to find the component of vector A along vector B if vector A is -1, 4 and vector B is 2, 7. Okay? So just a little extra practice. So A along B. So here we want to take the dot product because here we're not given an angle like the last problem was. So we want to use our vectors that we know so well. So dot product, -1 times 2 plus 4 times 7. And then the magnitude of B would be 2 squared plus 7 squared. So I get -2 plus 28. And then 4 plus 49. So 26 over the square root of 53. And so then that would be my component of vector A along vector B. Okay? Have fun.